One of the best geologic examples of physics in action is isostasy. You might know the density and height of the Earth's crust will affect how much sinks or sticks out above the mantle, but this video will help explain the awesome physics forces at play that lead to all sorts of amazing geologic features of the Earth's crust. We can ask a lot of questions here. Buoyancy, sinking, floating, but before we get ahead of ourselves, we're going to go back to the basics. Forces. You've probably heard of pull forces like gravity. It's what keeps us from floating off the planet, so pretty important, but we can break it down a bit. A mass is a volume times density. Look even closer, and a volume can be an area times the height of an object. So area times height times density is mass. And density is so important that we're giving it a fancy name, rho. Whenever we have acceleration, we have some sort of net force. But what if things aren't accelerating? Let's say we're holding up some blocks of water. We're pushing up, and the water is pushing back down. This may be weird to consider, but the layers of water are doing the same thing. Each arbitrary layer of water has a weight pulling it down. In order not to condense into the layers below, it must be held up by an equal push force. In fact, whenever anything, even fancy rock, floats in water, it must also balance out with the same push force of the water beneath it. This is how we define buoyant forces. The force of anything sinking into water is the same as the weight of the water it displaces. Let's look a little closer at this equation. We can get rid of the gravitational constant, so we're really just talking about the mass of the rock. If it has an area and a height, as well as some density, we can set those variables equal to the mass. But since this area pushing down on the water is same as the area of the water pushing up, the a variables cancel as well. Now we can simplify to a much prettier equation that gives us delta z. The depth into the liquid, the rock will sink. Because of the physics at play, this equation tells us that a thicker rock will sink deeper and vice versa. And a rock with higher density will also sink deeper than a rock with lower density. Now we've proven the general principle of isostasy. Not too shabby. But we can go even further. How much will the thickness and density of the rock really affect how much sinks? Let's start with changing the density of a rock that, like the continental crust, floats a bit above the surface. We'll call that floating bit h, or x minus delta z. It's important to remember here that x and delta z are not always the same. In fact, they're only the same when the densities are equal, so that this equals 1. So if the rock was just water again, it would line up right with the level of the rest of the water. Hopefully this isn't too surprising. Back to the rock. If we rearrange a little bit, we can get this formula in terms of the ratio of densities and the ratio of the uplift, h, over the total thickness of the rock. Okay, now what if we compare rocks with different densities? Let's say we have two identical rocks, but change the second one's density to half that of the first. What happens to its uplift, h? Let's do the math. Say we're looking at a rock that originally was 1/5 out of the water. The first thing we can do is figure out how dense it was compared to the liquid. Now, since we're decreasing that ratio by half in the second rock, we can quickly solve to see that the new uplift will be 18, over 3 times that of the first rock. We can use this equation with any rock, but this example shows us how important density is, and how much it can change what we see above the surface. This equation can also show exactly how much what we see is affected by the total thickness of the rock. If we don't change the density, then this whole side of the equation is constant. That means that the ratio of h over x is constant too. Let's see what this looks like for our rock. If all of a sudden you're walking along the continent and suddenly see the crust rise twice its original height, what's happening below the surface? If you can figure out that the rock has uniform density, it's composed of the same material, and these density ratios aren't changing, then, since h over x must be constant too, the total thickness of the rock must have just doubled. So unlike changing the density, changing the thickness even a ton will result in only a teeny change up top. We've answered a lot of questions here. Is isostasy magic? No, it's physics. But if you ask me, the physics of isostasy are just as enchanting.